So, I did flux for shell model, you can do similar thing for Navier-Stokes. So, what is the idea? So, the formula is, so is that wrote, so this is a sphere of radius k naught. So, pi k naught is two sums. So, giver p is within the sphere, p less than k naught, less than equal to k greater than k naught, k dot uq, up dot u star of k, imaginary part of this. Okay. So, this is a formula derived by various authors. We have some interpretation of this which is interesting, but I will not, it is not required here. I need to compute this integral. Okay. This formula we derived it. Okay. So, let me say we take a claim that this form is done by first time by Dar, my PhD student, Ishwaran and me in 2001. So, anyway, so we use this formula to compute flux. Now, I will not do the full algebra which is very involved, but you can see that there are 3 u's, right. We have uq, up and u of k. They are vectors. So, I need to do this tensor stuff, but essentially we have these 3 u's and this is a prefactor. There will be a vortex term. So, if you understand the shell model calculation properly, then you can do this calculation here as well. So, to 0th order, assuming u to be Gaussian, if I do the average, so I want average of this. If I do average, what will I get? To 0th order is Gaussian. So, odd order should give you 0. So, 0th order this integral is this product is 0. Okay. That is the equilibrium solution, but not the non-equilibrium solution. So, 0th order it gives you 0. So, I want non-zero value for the flux. So, what do? I expand it using Green's function. So, idea is, so there are three Green's function, sorry, there are 3 Feynman diagrams. So, one of them look like that. So, this g of q t minus t prime and the 2 legs will come, right. So, like before, so Green's function and 2 u's, Navier-Stokes equation has this 2 u's in the right hand side, and you get non-zero values only when this is up and the u of minus p, this is u of q, the u of minus q, and the 2 integrals, the 2 sums, right. So, that becomes integral. So, the 2 integrals here. Of course, there are 2 more Feynman diagrams which are like this plus like this. So, what is this integral? So, let us write the integral. Okay. So, dp dk. So, this p is sum and k sum. Of course, one of them is within the sphere, other one is outside the sphere. Okay. That will involve complications, but we will ignore that part. So, there are 2 correlation functions Cp, Cq t minus t prime, Cq t minus t prime, Cp, sorry, Cp, Green's function q t minus t prime, integral dt prime 0 to t. Plug in again the same form Ansat's assumptions. So, dp dk dt prime exponentials, right, exponential minus nu p p squared t minus t prime. I am just going to write them together, nu p p squared t minus t prime. What about this? Plus nu q q squared, and the 2 correlation functions. So, Cp Cq, but they are equal time correlation, for which I am going to substitute Kolmogorov law. Understand the difference between equal time and unequal time? So, unequal time has this exponential factor multiplied by equal time. Equal time is t and t equal to t prime. So, that is a spectrum, no, that is a spectrum, and the Green's function will give you q squared, no, k squared, I made a mistake. Green's function, this k, right, this k. So, k squared nu k is nu k. Okay. If I integrate with time, what will I get? Like before dp dk. So, integral always gives you in the denominator nu p p square plus nu q q square plus nu k k square and c p c q, and there will be some prefactors. Okay, if I do the other sums, I will get again two correlation function, but denominator is the same. So, these guys will basically, here I will get C q C k and the other guy will give me C p C k. And the prefactors are different, no? These prefactors are different. Okay. Now, what do I do next? I substitute Kolmogorov formula for the correlation function, and it turns out, I will not do algebra here, it turns out the right hand side is proportional to epsilon and a constant, and lo and behold, key Kolmogorov 3/2 by nu star. Okay, it's exactly same form, because dimensionally we should get the same answer. Okay, this constant will be different by stuff. So, this epsilon, so that means the flux is constant and equal to epsilon multiplied by a constant. So, this will cancel, but this constant, this guy must be equal to 1, no. So, I know nu star, this constant will come from the integral, complex integral. So, that will give me k Kolmogorov, and that is approximately 1.6, 1.7. Okay. So, if I do all this algebra correctly, then I get this Kolmogorov constant. Okay. So, that is the outcome of flux calculation. Okay. So, let us summarize. I think it is so RG analysis gives me nu k. It turns out nu k is not just for fun. This nu k is also very useful for real simulation, which is called large eddy simulation. So, we can define viscosity at different scales, also for modeling diffusion in atmosphere, right. So, I need nu k for atmospheric diffusion. So, all that can be done. So, enhanced viscosity. A flux analysis shows the flux is constant in the initial range. Okay, I showed you for field theory, and we can compute Kolmogorov constant. So, this scheme I believe gives me around 1.6 something, but if I use some different field theory, then I get different numbers, but they are all lying in this band, okay, which we find in simulations as well if you do carefully. Okay. These are non-equilibrium feature. Equilibrium feature exactly like what I argued for shell model. We can show that these correlations will be 0 for the flux. So, the energy flux will be 0, and other, well, for the viscosity is pretty somewhat complicated, but we can also show that nu k is not renormalized for Euler equation. Okay. The proof is a bit complicated, but it can be shown. So, we basically field theory is telling us same story what we expect. Okay. So, this is a non-equilibrium field theory for turbulence. Okay. So, let us stop.